It's happened at least 5 times in the history of our planet. Mass extinctions. Death on an unimaginable scale.
It's not just killing a bunch of individuals, it's killing every individual in the species that makes that species extinct.
These catastrophes were rapid global events, leaving their mark in ancient rocks.
So when you see the rapid disappearance of massive numbers of species in the fossil record, the question that's provoked every biologist is, what the heck happened? What's it take to wipe out most of the life on the planet?
As scientists hunt for clues around the world, 2 of the greatest extinctions may finally be solved.
Major events in the history of life have coincided with these extinctions.
What might these calamities tell us about our future? Are the forces that ravaged life eons ago back at work today?
If environmental change is great enough, fast enough, and on a global scale, the entire planet is in trouble.
Are we on the brink of another mass extinction? When you walk through the Smithsonian's National Museum of Natural History, much of what you see is extinct. But while species come and go, on rare occasions, there are mass extinctions. Rapid events that wipe out the majority of life on Earth. This is the story of 2 of those catastrophes, how they unfolded, and what they can tell us about our future. The first mystery is the death of the dinosaurs. 66 million years ago, giant pterosaurs ruled the skies. While beneath the waves, predators called mosasaurs prowled the seas. And dinosaurs roamed the land. Then suddenly, they were gone.
This is femur of a triceratops, so...
To understand the causes of mass extinctions, evolutionary biologist Sean Carroll has circled the globe.
Just hanging out, you got an edge-on view of the bone.
Mass extinctions pose the greatest biological murder mysteries. What killed the dinosaurs? Perhaps you've heard that we now know. But how do we know? Well, it required some of the greatest scientific detective work ever. And the trail began almost halfway around the world.
This is Gubbio, a sleepy Italian town. Not a single giant reptile in sight. Still, the past is everywhere you look. And beyond these walls, an even deeper past is buried. Just outside of town, there are traces of the dinosaur's world, its history written in the layers of limestone cliffs. Millions of years ago, these rocks were at the bottom of the sea. In the 1970s, American geologist Walter Alvarez was studying these limestone layers, analyzing fossils left by tiny shelled sea creatures. Called foraminifera, or forams for short, they're among the most common ocean plankton. When they die, their shells become part of the sediment and can be used as markers of geologic time. But Alvarez saw something striking. They seem to disappear at this mysterious line of clay.
You could see that in the top layer of limestone, there were fairly large forams. Then there's this clay layer, and above it, in this limestone layer, almost all of those forams are gone. And I think that sort of woke me up, because that extinction of forams, as close as we can tell, it's the same age as the extinction of the dinosaurs.
Almost 1,000 miles away, there was a similar pattern. On the Atlantic coast of Spain, Dutch geologist Jan Smit was studying forams as well. Their fossilized shells formed these limestone cliffs, just like in Gubbio.
So right there towards the boundary?
Right there, it's the boundary.
They represent the geological period when dinosaurs last walked the Earth. And like Alvarez, Smit found a puzzling clay layer marking the extinction of the forams.
Jan, what can we tell about Earth's history from just looking at these rocks?
Well, you can see the end of the one world and the beginning of the next one. And you see there is a very sharp, extremely sharp dividing line between the two.
That gray band.
That's that gray band over there. And all of a sudden we see a dramatic change, which we call the KT boundary.
The KT boundary lies between two great ages of animal life. The age of reptiles, with dinosaurs, and the age of mammals, after the dinosaurs were gone.
And the KT boundary, it's right here where you see a contrast between the purple and the dark. So here's plenty of life, and there the base of the food chain of the oceans disappeared. And everything which is dependent on it is totally zapped right at the boundary.
As soon as you see that extinction, it's very dramatic. They disappear without a clue. So you know it's important. We're looking at one of the major points in time. But you see, nobody has witnessed it. So we're looking for silent witnesses in the rock, and the first thing that comes to mind is this beautiful clay layer.
Varying in color and thickness, the layer was found around the world. Walter Alvarez also believed it was a silent witness to the end of the dinosaurs.
And that's what's beautiful about rocks, is that they lie there for millions of years and don't change, and they remember what happened when they were formed.
To unlock those memories, Alvarez sought help at the University of California at Berkeley from a Nobel Prize-winning physicist, his father, Louis Alvarez.
Alvarez looked at this layer and he thought there must be clues there. It was like Sherlock Holmes, seeing something odd. He wanted to know everything he could know about that layer.
Alvarez and his son hunted for chemical clues. What they found stunned them. The clay contained high levels of an element rarely found in the Earth's crust, iridium. Other KT sites had iridium spikes just as high. Louis Alvarez thought he knew why. Thousands of asteroids cross the Earth's orbit, and many contain iridium. What if one hit the Earth 66 million years ago?
So Louis Alvarez had this hypothesis that an asteroid would cause this destruction. He had the clue, the amount of iridium at Gubbio. Under this hypothesis, it would be spread all around the world. So now he could calculate how much iridium there had been laid down over the entire Earth. Now, he also knew how much iridium there is in asteroids and comets, so he can now calculate the size of the object.
The asteroid was 6 miles wide, weighing hundreds of billions of tons. Still, compared to Earth, it was tiny. How could it wreak such havoc? It would have hit at nearly 50,000 miles per hour. The energy released would be equal to about 100 million nuclear bombs. A huge mass of superheated debris would have been blasted into space, orbiting the Earth before raining back down. The Alvarezes thought the dust could have blocked out the sun for years, devastating life. This was the asteroid impact hypothesis for the mass extinction. A big idea that was just too big for some.
When the Alvarez hypothesis was first proposed, it was difficult for many scientists to accept, because for almost 2 centuries, geologists had crafted their worldview around a gradual picture of slow but steady change in the Earth without major catastrophes. Now, they were hearing a proposal that something had come from outer space and rewritten the history of life in almost an instant.
If an asteroid 6 miles in diameter did strike the Earth, where was the crater of the right age, type, and size? Alvarez estimated it was 120 miles across. But nothing turned up.
It was at least disappointing, and really it was embarrassing not to be able to find a crater that big.
With no crater, the next best evidence would be debris from the impact. Soon, beads of vaporized rock were found at some KT boundaries. And there was another critical clue: shocked quartz, formed only by violent explosions.
And it turns out that the size of the shock quartz increases if you go to North America. And so the chase for the crater was back on.
One of the most promising leads was discovered along the Brazos River, nearly 200 miles from the Gulf of Mexico. "66 million years ago, this was the bottom of the sea.
It's actually easy with fresh tracks.
In the 1980s, geologist Alan Hildebrand came to investigate an odd mixture of rocks at the KT boundary here.
So this is the typical mud just found in this area?
Exactly. All we see is 7 million years of this mud here. So, I mean, we're talking boring.
But this mud was full of protruding boulders right at the boundary.
So you had this really regular mud layer, and then all of a sudden this area that's just full of this whole mixture of boulders
And from different places. It isn't just the rock that was here in the seafloor. Maybe some of it got pulled from deep water, maybe some got pulled from shallow. It all got jumbled together and dumped here.
All right, so what could have happened here that would explain something so dramatic?
Well, had to be a hugely energetic wave in the ocean, a giant tsunami.
An asteroid 6 miles wide would have caused tsunamis hundreds of feet high. Traveling at the speed of a jet, they would have ripped up the seafloor, leaving debris in the Brazos River basin. Hildebrand realized the strike must have occurred near the Gulf of Mexico. But where? The breakthrough came when he found a map made by geologists searching for oil. It revealed a giant buried crater on the Yucatan Peninsula. And a rock from the crater contained the signature of an asteroid strike.
and it was full of shock quartz too. So this evidence finally convinced everybody that indeed there was a big crater buried on the Yucatan Peninsula.
Discovered in 1990, it was named Chicxulub, after a village near its center.
The discovery of the Chicxulub crater was the ultimate evidence of the asteroid impact. Moreover, the crater was the same age as the KT boundary, and it was the size predicted by Luis Alvarez. We now knew for certain what happened on that horrible day. Love that little rock sitting up over there.
Yeah, there's a little cap up there.
Although the trigger for the extinction had been found, key questions remained. How did a single impact in the Yucatan wipe out so much life across Earth? Which species vanished? How did the world change? Answers were found in the Badlands of the Dakotas and Montana, in the Hell Creek Formation. Its eroding buttes hold fossils of plants and animals that lived during the age of the dinosaurs and beyond. When paleontologist Kirk Johnson found the boundary here, he could study the scope of the extinction far from the impact.
Kirk, how important was it to find the KT boundary up here in North Dakota?
If you can put your finger on the boundary like you can right here, what that means is you can ask the very simple question, how was life before the impact different from life after the impact? All you gotta do is look for the fossils below and compare them to the fossils above. And that's what we've done here for the last 30 years.
This arid landscape was once a wet, lush forest. Crack open some rocks, and you'll see the leaves of trees that flourished here over 66 million years ago.
There it is, look at that.
Look closely, and you can find fossils of turtles, fish, and small mammals that thrived in the rivers and forests. And then there are the bones of the dinosaurs.
So this is a plastered femur of a Triceratops. So around the corner is the Triceratops sacrum.
The clues to what happened here lie in the fossils and where they're found.
This is an ankle bone of a small meat-eating dinosaur. And nearby we found this bone, which is a bone of a much larger meat-eating dinosaur. Same bone. See the size difference?
Right.
And you find these bones, identify the animal, and pretty soon you start assembling the list of dinosaurs that are present at any given level. And the closer to the boundary you are, the more we address the question of how long the dinosaurs survive.
We now know that 22 types of dinosaurs lived in Hell Creek, including the mighty Tyrannosaurus rex. If some survived, their fossils would lie above the boundary.
We've now found several specimens that are very close to the boundary. And really what that's showing us is that even if dinosaurs are rare, if you look long enough, you'll find them when they were living on the planet. What we have not found yet is any dinosaur skeleton anywhere in the world above the KT boundary layer.
So no dinosaur survived the aftermath of the impact. Neither did 50 to 60% of other species. The catastrophe was even worse than the Alvarezes had imagined. Within 600 miles of the impact, death came quickly.
If you turn your oven on broil, open the door, put your hand into the glow bar, that's what the dinosaurs felt very soon. And they were probably broiled alive within an hour or so.
What happened next was a chain reaction. Falling ejecta ignited fires. Soot at KT boundaries shows that nearly the entire world burned. Smoke filled the skies.
And there may have also been a lot of sulfur blown into the atmosphere because the impact site in the Yucatan Peninsula had a lot of sulfur in it. And all of those things were abundant enough to obliterate the sun.
The destruction triggered a global ecological collapse. Acid rain decimated plants, the base of the food chain. Toxic gases released by the impact destroyed the ozone layer that protects the planet from solar radiation. With habitats destroyed and the climate radically changed, the age of dinosaurs was over. But as scientists would learn, there's more than one way to push life to the brink. Since an asteroid strike ended the age of dinosaurs, scientists wondered if impacts could have caused other mass extinctions. At Meteor Crater in Arizona, Sean Carroll and geophysicist Jay Malash pondered the question.
So Jay, about how many times has the Earth been hit by an asteroid large enough to cause a crater this big?
We live in a shooting gallery. There are thousands of asteroids that created this crater and much bigger crossing the Earth's orbit. The question is, how often do we get hit by something big enough to cause a mass extinction?
The answer is very seldom. After much searching, scientists found no evidence linking an asteroid strike to any other extinction event. There have been at least 4 other mass extinctions. So what could explain them? Especially the most devastating, which ended the Permian period, long before the rise of dinosaurs. Almost 90% of the planet's species vanished. That's why it's called the Great Dying. In contrast to our world, the Permian was an alien place. The Earth had one supercontinent known as Pangaea. The ocean was teeming with life. There were trilobites, which had survived for eons, and creatures like the helicoprion with its saw-like jaw. There were no dinosaurs yet, but carnivores like the gorgonopsids, the first animals to evolve saber-like teeth. And plant eaters like the dicynodonts. So common, their fossils have been found everywhere. Then, suddenly, the world was almost emptied of creatures. What could explain it?
Without evidence of an asteroid, some of the old suspects came back up again. Could it have been a supernova? Could it be gases seeping from deep parts of the Earth? Could it be volcanism? What could possibly eliminate that much life in a short period of time?
In southern China, key clues lie buried beyond these ancient mountains. Here, scientists are searching for victims of the Great Dying on the banks of the Red River. Among them is geologist Sam Bowering.
The reason we came to southern China to examine the end Permian extinction is that we're faced with a very fragmentary record of rocks around the planet. And southern China just happens to be a treasure trove of end Permian rocks.
Whoa, beautiful.
Unearthing fossils from the extinction is the life's work of paleontologist Xu Zhangshun.
This one is different, but those 3 may be the same thing.
He's documenting which creatures lived and died here.
After 10 years of work, we've discovered that this cross-section has recorded the entire process of the mass extinction, the diversity of creatures that thrived in the Permian, and the sudden point where they disappeared quickly.
A half-mile upriver, the team has found the end of the Permian world and the dawn of the age of reptiles, the Triassic period.
Oh yeah, beautifully preserved.
Yeah.
What we have here is an exposure of the Permo-Triassic boundary. Now you might say, what's so special about this? You wouldn't know at first glance, but in fact the rocks to the right are Permian age rocks full of fossils, and this black shale, which is the Triassic, which has none of those organisms. And the line between them represents the greatest extinction in Earth history.
The black shale marking the extinction reveals a sick ocean.
In the early Triassic, the ocean appeared to be starved of oxygen. The water was highly acidic, and temperatures were rising. Such an environment was not suitable for many creatures.
What powerful event unleashed these changes? To solve the mystery, they need to figure out precisely when the extinction occurred. Just above the boundary, there may be an answer. A layer of ancient ash from a nearby volcano, full of time-telling crystals called zircons.
The mineral zircon, it's a famous gemstone, but it has a very unique attribute, and that is that when it forms in a magma, it's like starting a clock.
A clock based on radioactive decay, which can tell when a volcanic rock was formed.
So this is the volcanic layer that is very close to the Permo-Triassic boundary, which is right here. So we're going to separate zircons from it. We're excited about this one in particular because we are going to get the best estimate of the age of the Permo-Triassic boundary.
Yeah, this is just here we found actually.
Once the team dates the boundary, they can figure out when the extinction began. Then they can look for events that happened at the same time and zero in on the likeliest suspects. Back in the US, scientists follow another trail of evidence. In rocks from the boundary, there's an intriguing clue. A sudden change in the type of carbon, evidence of a dramatic global disturbance.
When we saw this disturbance, this indicated that there was probably a rapid addition of a lot of carbon dioxide gas to the atmosphere. And that's worrisome because carbon dioxide controls Earth's climate, and so the amount of carbon dioxide gas in the atmosphere has a very strong effect on how warm or how cold the planet is. So the big question that came up in our minds is, where did the carbon come from?
One prime suspect lies in the vastness of Siberia. Around 250 million years ago, a series of massive volcanic eruptions ravaged more than 1 million square miles of land. The Earth's mantle spewed out enough lava to bury an area the size of the continental US under a layer at least 1,000 feet deep. Huge amounts of gases, including carbon dioxide, poured into the atmosphere. Sam Bowering and a team of scientists have come to this remote area to search for remnants of the eruptions, known as the Siberian Traps. Much of the volcanic rock lies buried underground. To reach it, the expedition will travel down rivers that have carved through the ancient lava.
The beauty of being on this river is that we are able to float through time. And we're going to go up through the Permian, and then the last bit of the Permian is covered with this thick outpouring of lava that we know as the Siberian Traps. And we need to evaluate once and for all, does it coincide exactly with the extinction, or is it post the extinction, or does it significantly predate the extinction?
After days of traveling, geologist Lindy Elkins-Tanton makes the first discovery.
That is lava. This is material that's filled in around, see that edge right there? That's
A layer of ancient lava beside rocks from the Permian world.
This is the first moment in this whole trip where we've actually found the lowermost lava where it is in contact with the upper Permian sediments that it erupted onto. And so right on this interface is where we think that the Earth started to change.
Clues to this change must be here.
You got some, am I keeping these?
Yeah, hang on to this.
Sample looks good.
As well as zircons to date the eruptions.
Brad's too.
But collecting the evidence will take endurance.
There's nothing like riding in a boat with a cloud of mosquitoes around your head and driving rain.
You need some things to make you realize you're in Siberia.
The vast amount of lava is striking.
We've walked this whole distance and looked at this big cliff, huge amount of rock, and on it goes, outcrop after outcrop across a big part of Siberia. So there's nothing on Earth that's making rocks like these now on this scale.
After multiple expeditions, the hunt for evidence is coming to an end. Now, it's time to figure out if the greatest volcanic eruptions in Earth's history caused its greatest mass extinction. In Cambridge, Massachusetts, the evidence has arrived. Will it link the Siberian eruptions to the Great Dying? The first task, to isolate the zircons, the time-telling crystals that record history.
Zircon is absolutely a little time capsule, and if we can find those zircons in a rock, we've got a great chance of knowing to an amazing level of precision when that rock crystallized from a melt.
After figuring out when each zircon was formed, the scientists have a range of remarkably precise dates.
It's an amazing thing. What we've been able to show from our work in South China is that the mass extinction occurred very quickly and over a very short duration here.
251.9.
And we can show from our Siberia trips and the zircons that we've dated that the Siberian eruption occurred at the same time as, or even just a bit prior to, the onset of the mass extinction, and that's a very important result.
When you have two events in Earth history, both short duration, exactly the same age, it doesn't get any better in terms of finding the smoking gun.
It's powerful evidence that massive volcanoes in Siberia triggered the Great Dying. Even more surprising is the speed of the extinction. Instead of happening slowly over millions of years as once thought, it unfolded in less than 60,000. But how could eruptions in Siberia affect the entire world? crystals within ancient lava may contain the answers. In them, Ben Black has found tiny droplets of magma that, amazingly, still contain gases from 250 million years ago.
You can see the crystal that we're analyzing right here. And over here you can see the actual gases that were trapped inside this crystal. So the brightest orange colors show the most sulfur here, and then these green show you where there's gases like fluorine, and we find chlorine, carbon, which would be carbon dioxide.
So it's trillions of tons of gases released into the atmosphere. And we take all the evidence and we put them into global climate models. And we ask the question, can that much gas change the climate to such an extent that it would kill all the things that we know that it killed? And it looks like that's what it takes to make a global extinction event.
Our picture of the Great Dying is now clearer than ever before. As magma rose to the surface, it heated sedimentary rocks, releasing massive amounts of climate-changing gases. Among them was carbon dioxide, which traps heat. As the world grew warmer, ocean currents may have slowed, cutting off the flow of oxygen, creating dead zones. Excess carbon dioxide triggered ocean acidification, preventing animals from building shells. The changes were so overwhelming that most creatures could not adapt. So what can extinctions of the past tell us about our world today?
What's really valuable about comparing these mass extinctions, the KT and the end Permian, is they were caused by totally different triggers, right? An asteroid from above or volcanism from beneath. But they had very similar effects in terms of catastrophic destruction of ecosystems around the world. And there's a really simple lesson that's relevant to today, which is if environmental change is great enough, fast enough, and on a global scale, the entire planet is in trouble.
Humans are rapidly changing the Earth. Could life be at the brink again? Mass extinctions eons ago may seem as if they happened on a distant planet. But this is the same stage, even if the actors have changed. We're now in a third great age, known as the Age of Mammals. During this time, life reached its greatest level of diversity. But there are fears that the world could face another mass extinction. Only this time, instead of volcanoes or asteroids, the trigger would be us. Paleontologist Anthony Barnosky is investigating if the sixth mass extinction has already arrived.
Humans used to be part of nature. Now we're a force of nature. We have transformed 40% of the planet for our own needs, and things are only going to get worse because we're going to have 3 billion more people on the planet by the year 2050.
Across the world, vast regions of forests, home to most biodiversity on land, have disappeared. Other habitats are also vanishing. 70 years ago, the African savanna was home to 400,000 lions. Today, only around 30,000 remain in isolated patches.
We're doing two things to other species now. We're taking away where they live, but we're also separating their neighborhoods. And the problem is that we're changing the climate at the same time. So the normal response of a species would be just to move to a new home. They can't do that anymore because in order to move to a new home, they might have to go through Los Angeles.
Barnosky believes we're changing the Earth's atmosphere in ways that rival past mass extinctions. Just like the Siberian eruptions, we're releasing greenhouse gases that trap heat. Over the past century, CO2 levels and global surface temperatures have climbed, stressing ecosystems across the world. You can see the warning signs even in one of the world's most protected places, Yellowstone National Park. It lies within one of the largest intact ecosystems north of the equator, sheltering over 60 species of mammals. Among them is the grizzly bear, whose numbers have rebounded from 150 to about 600. But grizzlies are back on the endangered species list. Climate change is killing off one of their key sources of food, the high-fat seeds of the white bark pine tree. Across the American and Canadian Rockies, once green forests are bleached of color as white bark pines are killed by a tiny assailant. Biologist Elizabeth Hadley has studied the Yellowstone ecosystem for 30 years.
Okay, Sean, this is a great example. So, you know, if you look up, you see green branches and there's some cones up there. But in fact, this tree has just been hit. And the evidence are these little holes that are marked by red.
So the defense that this tree has is really minimal.
There's a sign here, there's a channel.
The culprit is the mountain pine beetle, which bores into the bark to lay its eggs. The newly hatched larvae eat away at the tree, quickly killing it.
So this is the beast causing all the trouble. Look at that, not even as big as my fingernail.
Beetles have long lived here, but as the climate warms, they're moving to higher elevations, attacking trees once out of reach. An average increase of just a couple of degrees means the winter is no longer cold enough for long enough to kill off the beetles. And it's all happening very fast.
This is what an attack looks like 7 to 10 years later.
Wow.
The last time I was here, this was a dense green forest with a cacophony of sound. Within 10 years, this forest is silent. These trees are not going to produce cones for at least 50 years. That is, if white bark pine comes back.
So the change may be permanent.
And bears aren't the only losers. Climate change of just a few degrees is threatening the web of life. Species around the world are moving, if they can. Even more worrisome, temperatures may rise by 9 to 11 degrees Fahrenheit by the end of the century. A rise almost as great as during the end Permian.
And the uncertainty is not that the climate is warming. The uncertainty is what the effects are going to be. Things that surprise biologists, unexpected connections, or, for example, certain populations that are under certain stresses we didn't quite recognize, but the next stress may push them over the edge.
What's happening on land is visible, but what about beneath the sea? Along the California coast, there are signs that the CO2 warming the atmosphere is also dissolving into the oceans. changing their chemistry.
And it has the net effect of actually making those waters more acidic. And it's a huge problem for the marine creatures that live there. They rely on a certain water chemistry. If the waters get too acidic, they can't build their shells. In fact, we're already seeing that in the Pacific Northwest, where the embryos of oysters and scallops cannot survive.
If the current trend continues, scientists predict that by the end of this century, the rate of ocean acidification will mirror what happened during the Great Dying. By geological standards, this is change at a breakneck pace.
There are predictions that we will lose most of the coral reefs on Earth by the year 2070. Now, if we lose coral reefs, we're not just talking about no nice places to snorkel. We're talking about loss of 25% of the fish species in the sea that depend on coral reefs. We're talking about loss of 10% of the ocean's fisheries that we depend upon.
Habitat destruction, ocean acidification, rising CO2 levels and temperatures. Humans are almost as good as asteroids and volcanoes at wreaking havoc. So has the 6th mass extinction already begun? To find out, Barnosky analyzed rates of extinction in the fossil record and compared them to data tracking endangered species today.
I had a sneaking suspicion that if we were able to calculate extinction rates over human history of the past few centuries in the same way we calculated extinction rates in the deep time paleontological record, that it might not look so bad. I was totally wrong. Once we crunched the numbers, it turned out we really were seeing hugely accelerated extinction rates today.
In fact, at least 12 times faster than species normally die off. Today, a quarter of all mammal and 1/5 of fish and reptile species are threatened with extinction. Amphibians are vanishing even faster.
If we continued to lose species at the rate we've lost them over the last century, within as little as 200 years, we would see 75% of species we know about disappearing from the planet forever. If we continue doing things pretty much as we are doing them today, what that means is the 6th mass extinction is a virtual certainty.
I think the hardest question to answer is, what do we do? And particularly, what do we do as individuals? What can we do? Well, one thing we know that works are reserves. Set aside a large enough space of intact ecosystems and animals can thrive there. So we at least have to do that.
A global effort is now underway to connect wildlife habitats with land corridors so animals can move freely. One corridor being proposed would run from Alaska to the Yucatan and includes Yellowstone.
I just think it's really important for people to realize that this isn't a lost cause. Humanity is at a crossroads right now. We can either choose to keep the endangered species alive and avoid the 6th mass extinction, or we can watch the train wreck happen. We have a very narrow window of opportunity to fix this. Will we do that? I like to think we will.
This is the age of mammals, and we don't want it to end like the age of dinosaurs, particularly at our own hands. We don't want sort of the equivalent of T-Rex of yesterday, the grizzly bears of North America, or the lions of Africa, or the tigers of Asia, to disappear, only to be seen as stuffed animals in a museum. So the question is, can we, because we understand what's going on, do something about it?